So hello, welcome to this session, which is part of our Solver Vendor series. Today we're delighted to have Robert Ashford from Optimization Direct with us. He will present their heuristic solver ODH CPLEX, which is part of the GAMS distribution and can also be licensed directly via GAMS. Without further ado, I would like to hand over to Robert, and I hope you will enjoy the presentation. Robert.
Well, thank you very much, Stefan. I'm going to give you a whistle-stop tour of our ODH CPLEX product, explaining what it is, what it does, and why it might conceivably be useful to you, if not useful, at least of interest. It's certainly of great use to many of our customers. But to begin with, let me say a few words about Optimization Direct. We're a company which sells CPLEX software, provides consultancy to CPLEX customers, provides modeling expertise, and indeed, we develop our own technologies for optimization, in particular ODH, which I'm going to talk about today. And we are looking at combining machine learning with optimization to help us deliver useful information, perhaps even good solutions to models that would previously be quite inaccessible. So in summary, what I'm going to do is talk about some of the challenges presented by optimization these days, in particular, those of dealing with very large problems, large-scale optimization, and how we address these with ODH heuristics. ODH comes in two sort of packages. One is an heuristics engine, which we call ODH heuristics engine, and the other is a version of CPLEX within which ODH runs and helps. So effectively, we've got a new optimizer called ODH CPLEX. I will talk about some of the new features of our new release before moving on to discuss how it works, what its behavior is on problems from scheduling, supply chain, telecoms, and so forth. Many of the more academic listeners might appreciate some information about how it works on standard benchmark examples, and in particular, we'll discuss those from MIPLIB, which are considered to be open at version 7. Well, models seem to be getting larger and more complex. So much so that the ordinary standard, if you like, MIP branch and cut technology gets very, very stretched, or indeed fails to deliver anything useful. Many people suppose that the solution time grows with model size and complexity, and that's quite reasonable. And they further suppose that that growth is superlinear. I'm afraid the reality is somewhat worse than this. Let's look at how solve times vary with model size, and I characterize that by the number of binary or integer variables in a model that we have to deal with after the standard pre-solve procedure. So we have here a plot of solution times for the solution of models of differing sizes. Now, they are all submodels of the same big scheduling model. So their structures are all pretty much identical. They just simply have different data, and they're obviously different sizes. What we can see here is that when the models are fairly small, they solve quite quickly. By and large, they don't take long at all. And then when the models get to a particular size, the solution times start shooting right up. Now, what I did for the purposes of preparing this slide was to impose a 2-hour time limit on each solve. So you can think of that 7 to 200 there as being hitting the time limit. So we have everything's going smoothly, very easily, with the occasional blip. And then we get to a size level where things start taking an awful lot longer. And that's where the ODH technology might come in. So what is it? Well, it's a set of tools for dealing with these large, difficult problems, and they're designed to exploit the parallel hardware that almost everybody seems to have these days, even on a laptop, but obviously for number crunching purposes on a workstation or server. The idea is to produce good, usable solutions rather than necessarily proven optimal ones. And what it does is to break the big model, the model that the user has presented, down into submodels and use CPLEX for solving those. Now, the basic heuristics engine itself cannot be used to find solutions on its own, and those can be extremely useful. Many of our users use it for doing just that, but it doesn't give any kind of an optimality guarantee or percentage gap that people are now used to seeing to let you know how close it is to some kind of proven optimality. When the heuristics engine is run within CPLEX, however, in ODH CPLEX, we can use CPLEX to do the branch and cut and provide effectively a bound on solution values, just as it does normally, so that we can get an optimality guarantee. So we can think of that, this product as simply being CPLEX with ODH heuristics inside it. And it's very good at getting solutions. Now, the engine itself is presented to users and system integrators as a software library, and it's particularly designed for embedding into customer applications, such as GAMs. It's got a set of callbacks and controls to enable users to control its behavior quite carefully. And if you're that way inclined, you can drive it from C++ using the IBM concert interface and Java and Python. We support both Windows and Linux as operating systems. That's all on 64-bit hardware. We do not support 32-bit implementations. We have driver programs which are useful for running the heuristic engine or ODH CPLEX from the command line, and the source is given to our customers, so they've got great examples there of how the library might be called and how to control it, how to specify what options to use, and so forth. It comes along with a short PDF user guide and skeleton scripts to help you compile and link the product easily. Now, people often ask, how does it actually work? Well, it's essentially a solution improvement heuristic or a set of solution improvement heuristics, but obviously we've got to have an initial solution to begin with, and that may be quite hard to find. ODH heuristics itself has local search methods, and it combines those with what are known as Big M or phase 1, phase 2 techniques to obtain a feasible solution. Or, and this would be by default the case when using ODH CPLEX, we can run CPLEX instead. Or with ODH CPLEX, we do everything at once. So the ODH heuristics engine is running its local search and doing its phase 1, phase 2, or Big M approach while CPLEX is running. And whoever gets a feasible solution first says, we've got a solution, let's go. At that point, we set about improving our current solution. Now that's done by decomposing the original model into a set of submodels, which are obviously much smaller than the original model, and then using CPLEX to solve each of these submodels, not necessarily to optimality, just to get a better solution. And it's arranged so that each submodel is solved in a separate thread. And as the submodels are solved and new solutions become available, they're recombined to give you a solution for the whole model, and the decomposition is repeated. And this continues each time, increasing the submodel size, potentially increasing the submodel size when it decides that's a good thing to do. One usually finds that the first set of solutions are relatively easy to find. Then as the solutions you find start improving, and obviously the gap begins to close, those solutions become harder and harder to locate. So it's got to do more work, and that necessarily involves looking at larger and larger submodels. The decomposition technology that we use is quite straightforward, really. It can be specified by the user, and ODH will in fact infer a decomposition if the model has meaningful names attached to its decision variables, and the user gives it a few hints. Alternatively, as is the case here with GAMS, and we might even see this being used effectively shortly, it could be specified by the user via a callback in a very flexible way. Or if you're not bothered to do any of these things, ODH will infer decomposition itself from the matrix structure. The operation of parallel programs can be somewhat unpredictable, but we do have, and in fact we have by default, a deterministic mode of operation in which you're guaranteed to get the same solution path if you solve a model twice. Or if you're concerned only about getting solutions quickly, you can say, well, we're not bothered with that, just run in what we call opportunistic mode, where we don't bother synchronizing the various threads. So when one thread gets a good solution, it says, hey, I've got it, and passes it straight away to the other threads who use it immediately without bothering to synchronize. And that can, on some models, speed up the solution process considerably. We have one significant big user who almost always uses ODH CPLEX in this way. Now, at this point, before I go into what's new in our latest release, I think it would be useful to look at how ODH CPLEX actually works on a little example in which we tried to schedule the working of nurses in an hospital. So I'm going to break off from this presentation and switch screens to demonstrate how this goes. Okay, we have a GAM called nurses.gms, which I'll run through very quickly. I'm not a GAMS expert, so although I can see the structure of this model, it's been prepared by GAMS staff who are experts in the technology. We can still see how the model is stated algebraically. So let's have a quick look at this. Oops, sorry. Right. Okay, to begin with, as the case with most demonstration models, we start off by declaring some data. We've got data items for each nurse, their name, how senior they are, how qualified they are, how much I have to pay them, and that sort of thing. We've got data relating to what they're going to be doing each day of the week, and what shifts need to be filled. We've got data describing the hospital's operation in the various departments on the various days and shifts. So we've got a hospital which requires its departments to be staffed by nurses. We've got nurses with particular skills and attributes ready to staff them. The nurses themselves have got requirements about where they particularly want to work and who they want to work with. So the data here is set up in standard GAMS arrays. I'll just run through that till we get to the meat of the model, as it were, which is one in which we declare a set of variables describing what happens. Most important here is the assignment of each nurse to each shift, knowing which department it's going to be on, which day it's going to be on. So if you think of a shift as being some time slot in the week, then we've got our assignments of each nurse to time slots in given departments during the week. We've got a variety of variables looking at, for example, how long each nurse works, how long they work on average, whether they work more or less than average, some measure of the fairness of the assignment, and looking at costs borne by each assignment, by each department. Now, the idea is to minimize costs, basically, but including a weight for the fairness of the assignment and the total number of assignments. We want, ideally, to start the hospital with as few assignments as possible. That's the kind of simpler solution. So we have algebraic statements here, putting the model together in the way that will be familiar to most GAMS users. So here, for example, we have the number of assignments for each shift S being no more than the maximum requirement for each department. Now, having posed the model, we need to run it, and statements required to run ODH CPLEX and control it all here within the GAMS file itself. So to begin with, we say we want to use ODH CPLEX as the solver. Then we create a little file called odhcplex.op, which contains some options. The first one here is to say, let's see what CPLEX is doing as well as ODH. The second one says, let's use a callback for doing the model decomposition. And that decomposition is specified in this line here. Basically, we're saying to ODH, hey, look at each nurse as a separate entity and create submodels consisting of sets of those nurses. And further on, where there are statements telling GAMS to report on various key performance indicators, like total cost, total number of assignments, so forth. So that is a simple model. Let's see what happens when we try running it. Okay, I'm going to pause the run here in order to describe what the output from ODH CPLEX actually means. To begin with, we've got a header which says what the program is, and it also identifies which version of CPLEX is being used and basic characteristics of the hardware. Right, these lines here are produced by GAMS and indicate the resources available. What follows is a set of log lines produced by both CPLEX and ODH. In order to distinguish between them, the ones produced by CPLEX are prefixed by CPX : and those produced by ODH prefixed by ODH : So we can see what's happening. Now, both ODH and CPLEX set about using the CPLEX pre-solve to try and make this model easier to solve. And the pre-solves produce lines of output. And since both CPLEX and ODH are simultaneously using the CPLEX pre-solve, not surprisingly, the lines of output are pretty similar. So this is kind of what we should expect. They may not be identical, because one of the things which we need to decide is how many threads to allocate to CPLEX and how many threads to allocate to ODH. Now the run here is in fact on my laptop, which is a 4-core machine with multi hyperthreading, or SMT, symmetric multi-threading, manifests as 8 logical cores, and it is useful to use a thread in each logical core. So we're using 8 threads here, which are divided 6 to CPLEX and 2 to ODH. So the pre-solves are getting different numbers of threads, and will typically do different things with respect to, say, probing, and may also do different things with respect to aggregation. So there may be some differences here between the pre-solves. Okay, well, after ODH has finished pre-solving, it goes and squirrels a pre-solved model away to deal with it. CPLEX, though, discontinues on its merry path. And before ODH starts doing anything with the pre-solve, at least tells you how big the pre-solved model is. In this case, it's reduced a little from the original size model, which it gives you at the start here. So they've gone down from almost 6,000 rows to just over 1,000 rows. So the pre-solve has done a significant amount of work. We now see output from both solvers. They're doing different things at this stage. CPLEX is solving the root. We have got an initial solution from the pre-solve, so ODH does not have to worry about trying to use a local search heuristic or any such similar to produce that initial solution, and can go straight in as here to decompose the model. Okay, so these are lines here, sorry, from ODH. The ones up here are entirely from CPLEX. So it decomposes the model and gives you some idea about how good the decomposition is. As a general rule of thumb, the lower the decomposition score, which is a measure of the score of the decomposed graph with that of the original graph of the matrix, the lower that number, the more effective the decomposition would be. If that number got to be 0, we'd have, in fact, decomposed the model into entirely separate independent submodels. Of course, in practice, that never happens, but the more independent you can make the submodels, the better the thing will run. So we now start the improvement heuristics, and ODH tells you that it's using 2 threads, and it also tells you that it's running in deterministic mode. So the log lines produced at this point by ODH and CPLEX are very similar. We have columns representing the node that we're looking at, if we're looking at lines from CPLEX, or the thread if it's from ODH, the number of loads left in the branch cut search if it's from CPLEX, or in fact a measure of the problem size, which is described as divisor here for ODH, objective value of the current problem if it's CPLEX, or how infeasible it is if it's ODH, number of infeasibilities, and best solution found so far, which is the same for both solvers, and similar for both solvers will be the best bound. ODH doesn't do a best bound itself, it takes it from CPLEX. We're running in deterministic mode though, so there may be some synchronization lag between CPLEX finding a good bound and ODH picking it up. So the lines from CPLEX and ODH may not be either monotonic or the same here. Okay, now at this stage you can see CPLEX is still solving the root because we're at node 0. The plus sign there indicates that it's found a feasible solution, and that tells you what it is. Similarly, ODH is running and it is finding feasible solutions too. So, right after CPLEX found a feasible solution of 58,200, ODH found one of 58,286, but then went on to improve it to 57,000 or 57,500. And that solution will be picked up by CPLEX, and it's picked up there. You can see that solution is better than anything that CPLEX has currently found. And I'll just let the model run a bit more. And now we're into the branch and cut phase of CPLEX. The ODH phase is doing the same thing as it always does, but you can see that the CPLEX node numbers now are increasing beyond 0, and we've got a significant size of branch and boundary left to look at. The difference between the solution we had before and the best bound is known as the gap, and the relative such difference is the relative gap, which is expressed as percentage. So that 7.25% there says, well, the current solution is at least as good as 7.25% away from optimality. So if you took that solution, you know you could never do more than 7.25% better. As the solution process proceeds, then obviously we expect this gap to diminish, and it will do, but not necessarily monotonically because of the lags between both CPLEX and ODH picking up each other's information. And it is now down to 1.75%, and there we are, we finished, and the gap drops down to 0. At the end of the solve, CAMS produce information about the key performance, produce information about the solve process, and will write information about the key performance indicators defined. So that, in a nutshell, is a quick guide to the log from ODH CPLEX and shows you how the two technologies work together to their mutual advantage, of course. I'll now revert to the just describing, what's new in our current release. We've, as usual for optimization vendors, made some performance enhancements, and overall they suggest that release 5 is a lot faster than its previous release, sometimes up to 100% faster, of which I mean it takes half as long, not that it takes 0 times as long. Some of that gain is related to the new releases of CPLEX that we're able to use, in particular 20.10, which has just come out, although 12.10, its previous release, was a significant improvement on the previous release 12.9 from CPLEX. Various changes made to release 5 are, for example, in supporting what I call dirty solutions. That is to say, solutions in which the integer variables take values that are within some tolerance of integers, but are not actually integer. Now, by default, nearly all of the top commercial optimizers say that a variable is integer valued when its value is, say, 10 to the minus 5 away from the exact integer value. And that integer feasibility, if you like, is usually a lot larger than the feasibility that it requires on satisfaction of constraints and bounds, which is 10 to the minus 6. And it's often the case that if you say, well, let's fix these variables for their real integer values and solve, which is something that some some people like to do at the end of a solve. If you do that, then quite often you can't find it for the solution isn't feasible at all. In other words, we've only achieved feasibility by flexing what we mean by the integrality of integers. And such a flex solution is known as dirty in ODH speak. We can work with it, we can use it, even though it's not terribly useful probably for the customers. It's still a solution with equivalent integrality to anything produced by, say, CPLEX or any of the other optimizers, but it's hard for this decomposition algorithm to work with solutions that don't take exact integer values. Nonetheless, we can do it, and in doing it, we can improve the performance of ODH CPLEX on mainly mixed integer models where these intermediate dirty solutions can be kind of useful. We've improved the synchronization between our threads, both between ODH threads and between ODH and CPLEX. So we now get good performance using hyperthreading or virtual multi-threading on an ordinary 4-core laptop or workstation. We are more canny about how much effort we put into solving each submodel. In other words, we've got kind of smarter submodel management, which improves submodel throughput, increasing speed. We have at release 5, and as used by that GAMS model that we've just seen, introduced a callback through which the user can specify the model decomposition. We've improved our support for non-binary integer objects like special ordered sets, indicators, and lazy constraints. We work within MATLAB. We work within the DO CPLEX IBM Python system, and we also support Python ourselves. We've managed to improve our Java support, particularly under Linux, so thread synchronization is now much faster. Here you can see the results of using ODH CPLEX on a real model. This is a real custom model that arose this year, in fact only a couple of weeks ago, in which the customer wanted to solve an almost infeasibly large model, one with 750,000 binary variables in it and 12 million non-zeros. CPLEX grinds away on it, and this is a plot of CPLEX's progress, the red line, over the course of 8 hours. And as you can see, sort of solution slowly gets better, and it has a bound down here, which is a significant distance away from the current solution. So you've got dotted lines there representing the bounds and solid lines representing the solutions. And even after 8 hours, the gap there was still too large, really, for the solution to be used. If we worked hard and tuned CPLEX, this particular model class, we can improve its performance. And you can see that here with the blue lines, in which the gap between the solid blue and the dotted blue lines, being the solution bound, the tuned CPLEX optimizer, is significantly less than it is for the out-of-the-box untuned one. However, when running ODH CPLEX entirely without out of the box, no special tuning at all, we get a reduced gap very quickly, and usable solutions appearing only after a matter of maybe 2 or 3 hours, rather than having, with a tuned CPLEX to wait 8 hours plus to get anything that we can work with. So this sort of illustrates what you expect from using this technology on large difficult models. We're not necessarily going to close the gap to naught any faster. In other words, we're not necessarily going to complete the search, but in most practical cases, you're not going to complete the search anyway. What we are going to do is to get good usable solutions much more quickly. And that's the whole point. Now, here are some examples taken from customers in scheduling, supply chain, and telecoms of significant size, apart from perhaps the easy one. And they're models that standard branch and cut technology finds quite hard. So if we characterize the size of the model by the number of integers in it, you can see the easy one there has only got, say, 58,000 integers. The telecoms model there is up to almost 13 million integers. So there's a kind of range of sizes, but they're all, even the easy one, quite hard. If we run ODH CPLEX on it and compare that with CPLEX itself, usually ODH CPLEX does quite a lot better. It happened that for the easy problem, CPLEX won. And that's in line with kind of what you'd expect, because the standard branch cut technology is designed to work well with models that it can solve to zero gap. So if your model is small, and you want to solve it to complete optimality, then it's going to be hard to beat an optimizer that's designed to do exactly that. However, if your model is not so small, you just want a good solution, the situation is quite different. And you can see here that for the supply chain model, the mixed model, ODH gets a 1% solution in 14 minutes, whereas CPLEX took over half an hour to do the same. After 8 hours, solutions were pretty comparable. Which is again in line with what you'd expect. If you run it for long enough so you effectively complete the search, then ODH CPLEX will probably look very similar in terms of performance. Now, for the more difficult models, the difference is even more stark. For this difficult scheduling model here, we had a solution. I mean, it's not a great solution, but it is a solution after 8 hours, and CPLEX hadn't found any at all. In practice, the user of this model tends to run it for a day or two to get a good solution, and I think this model is one to which it's found a solution of about 750, after a day and a half, and that's a good solution value. The large supply chain model is one in which after 8 hours we've got a very good solution with ODH CPLEX, but not really a usable one using ordinary CPLEX. The difference is starker with the scheduling model phase 1, where again after 8 hours we've got an almost usable solution, but sadly with CPLEX we haven't got any solution at all. The large telecoms model, the vast model there with 13 million integer entities in it, is one where the two solvers are running much more neck and neck, I suppose. It happens. ODH CPLEX is doing slightly better, but not sort of vastly so. So this is on relatively modest hardware, a workstation with only 4 cores, running quite fast, admittedly, and running 8 threads on those 4 physical cores. This situation is similar, but not identical, if one uses their workstation with more cores on it, in this case a 24-core Intel Xeon E5 processor using 12 threads. Again, we can see significant advantage to using the ODH CPLEX technology on these larger models. Now, those are just a few big models. What does it look like on a wider range of models? And I have a few here, some from model system vendors, some from forestry management, healthcare, electricity generation, and so on. They're all significant models, models to which it's kind of hard to find good solutions. How do we get on? Well, compared to the standard optimizer, ODH does quite a lot better on most of them. There are a few exceptions. This is a typical experience of anyone running an optimizer on a set of models, or two or more optimizers on a set of models, where just through luck, one optimizer will win sometimes, and another optimizer will win on other occasions. So overall, ODH CPLEX is doing somewhat better. The instances where it doesn't are, of course, highlighted in red. We get a similar picture using 12 threads on our server, the previous results being with 8 threads on the workstation, where ODH CPLEX tends to perform better than ordinary CPLEX. So you've got to remember that the ODH technology is using the same CPLEX, 1210 in this instance, both itself and for the optimizer we're running against. So we are comparing apples with apples, very much like with like. Summarizing, if you looked at the average gap presented by ODH CPLEX, it's significantly smaller than that produced by the CPLEX that was run this instance inside it, so 6% versus 17.5%, and it's significantly smaller than it was for release 4. So the new ODH CPLEX is better than it was previously, and it's better than just running an optimizer on its own. And if you're interested in sort of doing things with statistics, we could say reasonably that we're running twice as fast now as we were previously, and we can see that 30% of that improvement is down to CPLEX. There's a similar-ish story on 12 threads, so just by chance, the 12-threaded runs give you pretty much the same speed up as the, give you pretty much the same average gap as the 8-threaded runs. That's entirely by chance. Again, bit by chance, we've got the same gap using CPLEX. In this instance, slightly less of a speed up going from release 4 to release 5. And in this instance, there wasn't much of an uplift from using CPLEX 1210 compared to the previous release 12.8 was used. Academically minded listeners say, well, it's all very well and good, but you know, there are user models and user models. Let's look at standard test models. And I thought in this instance it'd be useful to describe how ODH CPLEX works on the so-called open set of MIPLIB models, which is a public collection of almost 300 models to which optimal solutions haven't been proven. Of these 286 models, 257 were known to have a feasible solution before we started here with ODH, and that left 29 models to which no feasible solution had yet been found. Well, with fairly modest resources with computer and time, we tried ODH CPLEX on this set, and in fact we proved optimality to 13 of these models, or 16 of them, if I'm going to use my 24-core workstation using running 16 threads. And it found better solutions to any solutions that had previously been known, to over 100 of them on the workstations and 116 on the server. So that's in a limited time span of 2 hours. So you've got to bear in mind that when people deposit these models with MIPLIB, they might have spent days trying to find a solution or prove optimality or what have you. So we're giving a fairly limited opportunity here for ODH CPLEX to show us what it can do, and it seems to be effective. Furthermore, it found solutions to 5 of those models where no feasible solution had previously been found. So, just in brief then, on these difficult models, ODH tended to perform quite a lot better than whatever had been run on before, which was, I guess, an ordinary optimizer of any kind. And sometimes that difference was very substantial on these R-mine examples, which I think originated from one of our competitors. And that's obviously very pleasing. We got optimal solutions to 13 of these models as here, and 4 of them were solutions where we'd actually complete the search, 0-0 gap, whereas the others were only to within tolerance. The one in pink there is a strange model in which dirty solutions really do throw it, and solutions offered by just an ordinary use of an optimizer turn out to be infeasible when those integer values are fixed to exact. Sorry, the integer variables are fixed to the exact integer values. So by just flexing those integer variables by 10 to the -5, we can get completely different solutions. So this is the model here, which is really in the MIPLIB set because it needs to be addressed with much tighter tolerances to say anything meaningful. The other models will run with default tolerances. Well, they might mean something to academics who've spent time studying them. More importantly, if you're a user of these models, ODH enables you to get to grips with at least 7 more than you could do previously. And I've itemized those here, in which we've got gaps of less than 5%. Sometimes snake one with solved optimality. Models to which no solution better than 5% was previously known. These are some models to which we found solutions, not necessarily good ones, certainly not solutions that we know are good, except in one case here, reasonable solution, I suppose. But nonetheless, solutions where none previously were known. The more threads you have, the better the ODH CPLEX runs. And with 16 threads, we got a better than best known 216 models. We matched the best known solution in 51, and we were worse in only 90 models. This is the models to which feasible solutions were previously known. So, with just 2 hours runtime, that's, I think, something that is reasonably useful. So, in general, then, for performance, ODH CPLEX is relatively better than the standard optimizer the harder the model is. Even if they're not necessarily large, we can still get benefit from using it on small hard models. It's relatively better when using more threads, and it is certainly effective using 8 multi-threaded threads on a 4 physical core workstation. In terms of hardware performance, the bottleneck for this and almost any other technology is currently the bus speed. We'd love to use hundreds and hundreds of processors. The problem is they share the same bus. We get hung up on bus contention, and memory accesses really do slow the thing down. With ODH CPLEX, one sees a degradation in performance if one goes from, say, 36 to 48 threads on the 24-core workstation that we have. And it's going to be the same story, although the optimal performance may lie at a different number of threads on basically any other motherboard or bus technology. Right now, getting a fast bus speed, avoiding this kind of contention, would be the thing which improves computer performance the most. And lots of people are working on it, and have been promising results in the near future and have been doing so for a while now. We hope that they will report positively soon. ODH is available on the cloud, either private or public, and that can be useful because the kind of solutions you want might come a lot more quickly. In fact, they do on many problems, and that gives you saving if you're using the cloud on straight cloud costs. We have one customer who achieved a 75% saving on his cloud costs by using ODH CPLEX rather than just an ordinary optimizer. And another customer in a slightly different area got an even bigger gain, whilst still getting solutions that are very close to optimality. So in conclusion, customers want to solve larger and larger models. There are unfortunately very hard barriers in terms of size to solving a model to optimality, or even getting a solution at all. The idea of ODH heuristics is to find those good solutions. It can be useful even on smaller sorts of models. ODH heuristics running within CPLEX as an ODH CPLEX can not only provide solutions with guaranteed quality in terms of optimality gap, we can get them quickly and possibly even outperform an ordinary optimizer to complete the search. One sees frequently that if an optimal or near optimal solution is provided at the root of a branch and bound search, the size of tree that needs to be searched will be much, much smaller than is the case if the optimizer doesn't have such a good start and good solutions are generated within the tree rather than at the root. Modern hardware is distinguished from hardware of 5 and 10 years ago, mostly by the level of parallelism that's available. And the idea of ODH CPLEX is to exploit these improvements as much as possible. And it does it as far as it can, and the only limitation really is in the memory bus speed. If you think that ODH heuristics or ODH CPLEX would be useful, then we're happy to help you in benchmarking the product and evaluating it on your models. You can send us copies of your GAMS files, matrices, or you can ask GAMS for an evaluation copy of ODH CPLEX. Thank you very much for listening.